It's my pleasure to welcome you to the 2024 Morris Loeb Lectures in Physics. The Morris Loeb Lectureship was established in 1953 by the Department of Physics under the terms of the bequest of Morris Loeb, AB 1883. The Loeb lecturers are chosen by the department faculty and are invited to visit the department to present 3 lectures and meet with the faculty, students, and scholars. After the lecture, we might be able to devote a few minutes to questions and answers, but please raise your hand to ask a question and wait until you're handed a microphone to speak so that your question is recorded. All right, so now let me introduce our speaker, Fiala Shanahan. She grew up in Adelaide, Australia, and obtained her PhD from the University of Adelaide in 2015. Before joining the MIT physics faculty in 2018, Professor Shanahan was a postdoctoral associate at MIT from 2015 to 2017 and held a joint position as assistant professor at the College of William and Mary and senior staff scientist at the Thomas Jefferson National Accelerator Facility from 2017 to 2018. She has been recognized by a number of awards, including the Maria Goeppert-Meyer Award from the American Physical Society and the Bragg and Ruby Payne Scott Medals from the Australian Institute of Physics. So today, she'll give the first lecture of the lecture series titled The Building Blocks of the Universe, Proton and Nuclear Structure from the Standard Model. Please.
Thank you very much. It is an absolute pleasure to be here, and I didn't have to come far, just from down the road. Okay, so this talk is really about the structure of matter, and in particular about the structure of the protons, neutrons, and atomic nuclei that make up the majority of the visible matter in our universe. Now, we know our modern understanding is, of course, that the protons and neutrons inside an atomic nucleus themselves have substructure. They're not fundamental particles. They're made of more fundamental particles called quarks, held bound or glued tightly together by the strong nuclear force, manifesting as force-carrying particles called gluons. To the best of understanding, that's it. There are no deeper layers of structure. The quarks and gluons are fundamental. Now, quarks, gluons, and their interactions are encoded in the standard model of nuclear and particle physics. The framework was put together in the 1970s, and it includes just 17 fundamental particles. So we have them here. We have the matter particles, the quarks. We have leptons, like the electron and its neutrino and their heavier cousins. We have force carriers for 3 of the 4 fundamental forces, so notably excluding gravity, as described by the separate theory of general relativity. We have the photon for electromagnetism, the W and Z bosons for the weak interactions, the gluons for the strong interactions, and of course, the Higgs boson. And the standard model brings them all together in this very beautiful, elegant, symmetric, and very predictive framework. So in fact, many of the particles of the standard model were predicted just from the structure and symmetries of the theory before they were ever seen experimentally. So just the most recent few of those was the W and Z boson, that was in 1983, the top quark in 1995, the tau neutrino in 2000, and then in 2012, the Higgs boson was the last piece of this puzzle to be seen experimentally at the Large Hadron Collider. Now, this beautiful, elegant, symmetric theory is extraordinarily successful. It describes almost everything we observe about the universe, and I want to give you just a sense for just how successful this theory really is. So here's just one example. This is the magnetic moment of an electron. That's how much torque an electron feels if you put it in a magnetic field. And the number I'm showing here is called the anomalous magnetic moment. That's the difference from the classical result, or the difference from the tree-level result. And what you see here is the most accurately verified prediction in the history of physics. You see beautiful agreement between theory and experiment to 12 significant figures. If there are grad students in the audience taking quantum field theory, you'll understand when I say this was a really heroic theory calculation. It's something like 5 loops, 30,000 Feynman diagrams, I think 12,000 Feynman diagrams, took about 30 years of effort to get this result to this precision. And it works. Beautiful, right? And it's not just this, of course. It's not just static quantities. The standard model is successful over an incredibly wide range of energy scales. So here's just one more example. Here I'm looking at deep inelastic scattering. So fire an electron at a proton so hard that it breaks the proton apart. you can describe that scattering process in terms of a number of quantities called structure functions. That's what we're showing here. And on the horizontal axis is energy, and this is a log scale. So here we're going over 5 orders of magnitude in energy scale. The standard model are these yellow lines here, and all the data points are from experiments, and you see beautiful agreement between theory and experiment over many, many orders of magnitude of energy. Okay, so wonderfully successful predictive theory of fundamental particles. But, of course, we also know that the standard model does not describe everything we observe about the universe. So just one example that we'll come back to later in the talk is dark matter. In fact, the standard model describes this small 5% sliver of the universe's energy density pi. About 5 times as much is dark matter. That it appears to be matter, it interacts gravitationally, but it doesn't emit or absorb light, hence dark, right? And everything else, well, we don't know what it is, but we call it dark energy. It's whatever's driving the accelerating expansion of the universe. So the standard model, as successful as it is, only really tells us about this little sliver here. And it's not just that, of course. Neutrinos have masses in nature. They don't in the minimal standard model. We know they have masses because experimentally we can see that they oscillate or change flavors as they propagate. And this is a beautiful undergraduate quantum mechanics problem. You get that when the flavor or the type eigenstate doesn't match the energy eigenstate with which it propagates. Right? Just a 2-state system. You can figure this out yourself. There's a matter-antimatter asymmetry that we can't explain. If the Big Bang starts and it creates equal amounts of matter and antimatter, and you allow only standard model interactions, we shouldn't be left with quite so much matter left over at the end. Everything is made of matter, right? We, the stars, the planets. Why is there so much matter left? Gravity doesn't fit in. How do you unify general relativity with the standard model? Open question. There's questions about naturalness. Why is there such a discrepancy between the weak and the gravitational scales, and so on? Right? So the standard model does not describe everything. And we make huge efforts as a physics community to find and constrain the physics that we know is there beyond the standard model. And so just one of the ways in which we do that is through experiments at what's called the intensity frontier. So these are very precise experiments. We look for, say, very small deviations between standard model physics and the experimental results that you can measure about the universe. So examples of this are, for example, magnetic moments. I just showed you the magnetic moment of the electron as the most accurately verified prediction in the history of physics, right? The magnetic moment of the muon, the electron's heavier cousin, there's a rather interesting tension between the sort of accepted theory result and the latest experimental measurements. It's 4 or 5 standard deviations. Some more recent numerical calculations of theory give a result much closer to the experiment. We'll talk much more about this later, how you do these sorts of numerical calculations of the standard model. But there's an interesting tension, which is potentially a test of the standard model or hints of new physics. Other examples in this category, we talked about dark matter. Well, dark matter direct detection experiments where you build a detector deep underground to shield it, and you look for dark matter to hit and directly interact. That's also an example of an intensity frontier experiments. Various other neutrino physics experiments all fall into this category. And what all of these searches for the physics beyond the standard model have in common is that you need to understand the physics of the standard model in order to be able to do them. You need the theory result to compare with the experimental measurement to find a difference. You need backgrounds and benchmarks for the experiments that you're doing to search for the beyond standard model physics. Right, so this is really what drives the need to start from the standard model and understand the structure of matter. It's firstly for its own sake, and I have to say I'm really excited about that. I want to know, how do we get from this beautiful theory, 17 particles, all the way to all of the complexities of nuclear physics? Can you go further? Can you go to nuclear physics? Can you go to chemistry? How does all of that complexity come out of this fundamental theory? But also, we know it's not complete, and in order to find the physics beyond the standard model, we need those backgrounds and benchmarks. Okay, so that's really motivating this quest, and it's also really the outline of the talk. So after a little bit more background, I'll give some examples of sort of recent developments in both of these categories in understanding the structure of matter sort of for its own sake, but also for backgrounds and benchmarks for searches for new physics. And then at the end, I'll talk a little bit more about how advances in computing and algorithms are feeding back in and really opening new windows in this space. Okay. So to talk about trying to study the standard model from first principles, we really have to talk about the strong interactions, which are described within the standard model by the theory of quantum chromodynamics, or QCD. That's because the strong interactions are responsible for binding the quarks together to make protons and neutrons, and binding the protons and neutrons together to make nuclei. So if I want to talk about the structure of those protons, neutrons, and nuclei, the strong interactions are particularly relevant, right? Unfortunately, they're also quite difficult to study from theory because the theory is non-perturbative. So at low energy scales, the coupling strength of the theory is large, and that means you can't use perturbative methods. So what that means here, let's look. This is the coupling strength of the theory. This is energy scale. As you move to the right, the coupling becomes small, and that means that you can do an expansion in powers of that coupling. You square a small number, it gets smaller still. Right? So you can go up to some order, you can say that's high enough precision, you can stop, you can make predictions in a perturbative manner. As you move to the left, and even further to the left than this plot shows, this coupling becomes large, becomes larger than 1. This, of course, breaks down. You square a large number, it gets even larger. Right? The theory is non-perturbative, you can't use these sorts of perturbative methods. So what we're left with is a numerical approach, which is the only systematically improvable first principles way of studying the equations that describe the strong interactions, so the equations of quantum chromodynamics, or QCD. It's called Lattice QCD, and it really is, at heart, exactly what it sounds like. You discretize space-time onto a grid, or lattice, in such a way that you can solve the equations of the theory numerically. Right? So, of course, the QCD equations, again, for students taking field theory, they're really described by path integrals. It's a quantum field theory. But what you can think of is when you're computing some observable, it's really an integral that when you discretize the theory onto a grid becomes a very high dimensional integral that you're trying to do numerically. By very high dimensional, I mean something like 10 to the 9 to 10 to the 12 dimensions. So this becomes a massive computational challenge to do these sorts of calculations. Right? They're done by sampling, right? Calculating the integral by Monte Carlo sampling. And because it's so high dimensional, you can't just do straight random sampling, right? You would need many samples, would be intractable. You have to do what's known as importance sampling, which is, again, essentially what it sounds like. You sample the most important contributions to the integral correspondingly more, and the least important ones correspondingly less. And why there should be more and less important contributions to the integral, you can get a feel for it just from quantum mechanics. We of course know that paths near the classical path are dominant and others are less important, and the same sort of feeling applies here in the quantum field theory calculations. Okay, so very high dimensional integrals that we're doing via sampling. And so just to be a little bit concrete, this is sort of as technical as we get about the lattice QCD here in this talk. You put your theory onto a 4-dimensional space-time grid. Of course, you have some finite lattice spacing. You have to take the limit as that spacing goes to 0 to get back your continuum physics. Of course, you have some finite box size. You have to take the limit as that box becomes large to get back to continuum infinite volume physics, right? So you have to do the calculation again and again on smaller grids and bigger boxes. And sometimes you might use different values of the quark masses than you have in nature. And I will show you some results with larger than physical values of the quark masses. The reason is just computational expediency. If you're trying to do something that's really at the edge of what's possible computationally, you can make the calculation a little bit easier by making all the quarks heavier and then extrapolating down rather than trying to do it directly. Right? I can see some people scratching their heads. The reason is basically that in doing these calculations, you have to invert very big matrices that get closer to being singular as the quark mass gets lighter. Singular matrices are harder to invert numerically. Right? So you make them quark masses heavier, matrices are less singular, easier numerical problem. Okay, so what it really looks like is I have an integral. It's a path integral in the field theory sense, but an integral here over quark and gluon degrees of freedom. I want to compute the expectation value of some operator here. Inside that path integral is the exponential of the action. That's the function describing the quark and gluon dynamics from QCD. I sample contributions with this exponential fraction already built in, so I sample them with that weighting. And then calculating the observables just becomes taking means and standard deviations over your object calculated on all of those samples. So it's really, in the end, a statistical problem. Right? Okay, so that's the approach. What's really important to realize is that the input to these sorts of lattice field theory calculations, the free parameters in the calculations are the same free parameters as in QCD itself. So that's the quark masses and the strong coupling. That's it. Once you've fixed those, and you have to fix them by matching to some number of experimentally measured quantities, so masses of some fundamental composite particles, so like a pion or a kaon, right, to set the quark masses. Once you've matched those, everything else you get are predictions from the theory. Everything from the proton's internal structure through to nuclear reactions or nuclear structure. There's no sense in which you have to take a nucleus and model it as protons and neutrons. Everything just comes out from QCD itself, the underlying theory with quark and gluon degrees of freedom. Okay, so I've sort of hinted that these calculations are extraordinarily computationally expensive, and they really are. So of course we don't run them on my laptop, we run them on the world's largest supercomputers. We have now exaflop machines in this country that give you a sense of scale. Some of the calculations that I'll show results of would have taken between 50 and 150,000 years on this laptop. It's a fairly good laptop, it's, recent model laptop, right? So really, really large scale calculations that often take many years. So some of the largest calculations you should think of like experiments. You accumulate data over a number of years, unblind the data and look at the result and do an analysis at the end. Nevertheless, despite this sort of extreme computational scale, the approach also works. And we're now really in a precision era of this method, at least for, say, simple aspects of the proton structure. So here are some examples from, it's about a decade ago now, so really the beginning of this precision era for lattice field theory. Here's an example of the proton-neutron mass splitting. Now, I want to demonstrate on this slide some examples of the complementarity between theory and experiment. The proton-neutron mass splitting, of course, you can measure that experimentally very precisely, right? That's this line here. So you say, well, why do you want to calculate that number from theory? You already know that number. We can measure it extremely precisely. What you can see from theory calculations is really where it comes from. So you can see how that value comes from the delicate interplay of the strong interactions pushing it one way, the electromagnetic interactions pushing it the other way for a cancellation that gives you precisely the value that you measure in nature. Right, we can understand where that mass splitting comes from in terms of the fundamental degrees of freedom. Another example on the right of this plot here, this is the spectrum of some heavy baryons. Those are particles like the proton, but with some heavier quarks inside them. And all of these different points correspond to lattice QCD predictions of where states are. The bars here are from experiment, except for this bar, I photoshopped that on after the fact. That was a lattice QCD prediction of where this state should be. The LHC experiments had not found it. After knowing where they should look, they went and found it precisely where it was predicted by the theory calculation. So again, an example of the real complementarity now that we're in this precision era between theory and experiment. We'll see that coming back again and again in this talk. Okay, so moving to some, I said those were about a decade ago from the start of this precision era, moving to some very recent examples. Okay, and for this talk, I've decided to really focus in on the quark and gluon structure of protons, neutrons, and nuclei. So what do I mean? Well, at the most fundamental level, we can say, well, how do the basic properties of the proton, its quantum numbers, right? Its mass, how do they come from the quarks and gluons? How does the mass of the proton, its spin, its momentum, how do they come from the more fundamental degrees of freedom? How do the quarks all come together to give you exactly spin half, right? So many of these questions we now can answer extremely precisely. So here's an example from a few years ago of the proton momentum decomposition. This is a first principles calculation, and it's showing what fraction of the proton's momentum comes from up quarks, down quarks, strange quarks, charm quarks, gluons, and you can add them all up and you get 100% within uncertainties exactly as it should be. Right? We can very precisely account for all of these contributions to the proton's fundamental properties. I want to go into more detail on what I think is a maybe more interesting question is, well, what about the three-dimensional structure of the proton? What is the distribution of the quarks and gluons inside a proton? Are the quarks and gluons in similar locations or different locations? Are their distributions similar or different? And on this front, there are some fundamental and even qualitative questions that we're only just beginning to answer within the last year or two, the last 18 months or so. And so I want to draw your attention to one in particular, which is the gluon radius of a proton. Now, if you talk about the size of a proton, you almost always mean its charge radius. That is the radius of the proton as seen by an electromagnetic probe, right? Now, the gluon does not couple directly to an electromagnetic probe. So in some sense, a charge radius is very much a quark radius of a proton. Tells you something about the distribution of quarks. And you might ask, well, what about the distribution of gluons? What do I expect? Should that be the same? Should it be different? And if you turn to models for answers, well, you get different answers. So I'm from MIT. If you look at the MIT bag model as your favorite model, you say, well, the gluons expand to fill the bag. This is sort of old school, right? The gluons expand to fill the bag, so the gluon radius should be bigger than the quarks that hang around in the middle of the bag. If you like a constituent quark model, that's where the gluons hide inside massive quarks, basically. We say they're at the same locations, so a gluon radius should be the same as a quark radius. If your picture is really sort of flux tube picture, and you might have seen pictures from Lattice QCD where you take heavy quarks, static quarks, and you pull them apart, and you can really see these flux tubes emerging between them. You say, well, gluons always come in between the quarks, so a gluon radius should be smaller, right? So intuition from the models gets you all sorts of answers. And so then the question is, well, what do I really mean by a gluon radius? How do you define that? And one of several ways you could go to define analogous quark and gluon radii to compare them is via, say, the pressure distribution inside a proton. You can also think of this as being from the energy density inside a proton. So let's draw a cartoon of, this is the center of the proton, and I'm moving out along a radial direction here. And quarks are confined inside protons, right? So if there's any sort of an expansive force, a repulsive pressure, then there also has to be a confining pressure, right? An inwards force, otherwise the proton wouldn't be stable. So I'm showing this particular quantity on the y-axis, this radial distance squared times the pressure, because this is the thing that has to integrate to 0 for stability. So it's easy to draw a cartoon. If there's a peak, there has to be a trough, so this whole thing integrates to 0, so the proton's stable, right? Repulsive pressure meant there also has to be a confining pressure. Okay, so this is about the only cartoon we could draw. Okay, we could have the peaks the other way around, or we could have multiple peaks, but it has to look something like this just from a cartoon perspective. And then you can start to ask questions. You can say, well, what's the peak pressure in a proton? Should you even compare that? Is it more like a bike tire that's 10 to the 5 Pascal, or more like the interior of a neutron star that's 10 to the 34 Pascal? Right, what about a proton? You can say, well, whoops, we skipped ahead. You can say, well, what is the radial extent of this pressure distribution? And importantly, does this picture look the same for the quark and gluon pieces, and do they have the same radial extent or not? So this is one way of defining what we might mean by a quark versus gluon radius, and getting at an answer to this question. So within the last few years, we've been able to make a version of this that's now not a cartoon, but actual data. So I'm showing exactly the same figure here, but now data. The blue here is the quark contribution to the proton's pressure as measured for the first time in an experiment at Jefferson Lab. The experiment was not sensitive to the gluon contribution, so it could only measure the quark pieces. In green, I'm showing the gluon contributions to the proton pressure as computed in a theory calculation by my group. And the theory calculation, we didn't compute the quark piece, we computed only the gluon piece. And so by combining theory with experiment, for the first time you're able to get a picture of the complete proton's pressure distribution combining quark and gluon pieces. And you find that the peak, the red is just the combination, the peak is more like the interior of a neutron star than a bike tire. That's interesting. But particularly interesting is that if you look at these tails of the distributions, the green goes out much further than the blue. So this was really a first hint that it looks like, by this definition, the gluons are extending the radial pressure distribution of the proton, extending the radius of the proton compared to the quark pieces. So this was, as I said, one part from theory, one part from experiment. You know, the very first time putting all this together, not everything fully controlled. This was the first hints. This was 2019. There have been a lot of developments since then, and the synergy between theory and experiment has really continued. So on this slide, I'm showing the fundamental distributions underlying those pressure distributions. Their quantity is known as generalized form factors. And we're not going to go into too much technical detail here, but the horizontal axis is a momentum scale. And these are two different generalized form factors. The Fourier transform of this one is related to that pressure distribution that I was showing. And this one here, well, this point here in the forward limit, that's the momentum fraction. If you remember that chart I showed you before, quarks and gluons are both carrying about 50% of the proton's momentum. Both these are the gluon distributions, the gluon being about 50% here is the same statement that I made before. Okay, so what you see here in this figure are first experimental measurements of the gluon structure of the proton. Those are all of the different bands, and all the different bands are from the same experiment. The experiment could not fully separate these two quantities, so different model inputs were used in the analysis, which gave fairly different results. Right? The lattice QCD calculations that we did give these blue points here, which you can see agree much more closely with one analysis of the experimental data than the others. So again, the synergy and complementarity between theory and experiment. Here, theory is giving input on, how to think about analyzing the experimental data. Okay, so I started this by saying, well, what about the radius of the proton? We can come back and really sort of quantitatively answer this question from these experiment and theory results now. You can define what are called mass and mechanical radii from these pressure distributions, just different ways of defining a radial extent from that distribution. And that's what I'm comparing here on this figure. This point, this distance here is the charge radius of the proton, what you usually think about as the proton size. In this panel are calculations and measurements of the mass radius. In this panel, calculations and measurements of the mechanical radius. So the first thing you see is, okay, good, they're all roughly similar. So the size of the proton is a somewhat consistent value. Here you see these red points. These are theory predictions for quark radii that had not been experimentally measured at the time we made them. This grey point was the first experimental measurement of that particular radius that came out just a few weeks after our theory result, and as you can see, it agrees very nicely with the theory prediction. So again, complementarity between theory and experiment. You can see the blue, which are the gluon radii, are consistently somewhat larger than the red, which are the quark radii. So we're starting to get more data to back up this sort of first hint that we had of the gluon radii being somewhat larger than the quark radii. And as you can see, these are results from 2023, 2024. So these are really very, very recent developments into what feels like a really fundamental question. What about the proton size? This is fairly new work. Okay, so I spent time talking about pressure distributions. I said the word pressure many times. Proton's pressure distribution. And you may have thought, well, one of the places I care about pressure is in neutron stars. So if you can calculate pressure inside a proton, can you calculate pressure in neutron-rich nuclei and use that as input into looking at the equation of state of neutron stars? And the answer is, in principle, sure. In practice, it's really, really hard. So actually we're working in this direction, but it's going to take quite a number of years. And the reason is doing these sorts of first principles calculations for nuclear physics are extremely computationally demanding. I talked about 50 to 150,000 years of computation on my laptop for the proton calculations. Well, the nuclear calculations are a product of an exponential and a factorial more expensive. Okay, so that gets out of hand very quickly. So why? So the noise, remember we're doing very large integrals by sampling. The noise grows exponentially with the size of the nucleus, the number of protons and neutrons. So you have to take exponentially more samples to get the same statistical signal. But the amount of work you have to do, the amount of computation you have to do on each sample grows factorially. You have to contract all the quarks together with each other. So you have to do a factorially growing amount of work on an exponentially growing number of samples. And so this becomes intractable very, very quickly. First calculations are possible for atomic numbers, so number of protons and neutrons up to about 4, maybe 5, right? And it just explodes from there. So trying to do this is something that we've been working on for a long time now, for more than a decade. This is work with a larger collaboration. It's called the Nuclear Physics from Lattice QCD collaboration, very descriptive name, which involves just a handful of faculty members. And we've been slowly working through showing how you can do lattice QCD calculations of nuclear physics over the last decade. So the types of problems that we've been interested in is proton-proton fusion. So that's the process that governs the burning of the sun. Tritium beta decay. double beta decay. So a very interesting process. If you could observe neutrinoless double beta decay, it would tell you whether the neutrino is its own antiparticle or not. Theory calculations could really guide experimental efforts there. They're really hard to do. How can you do them from Lattice QCD? Well, these are the types of problems we've been trying to answer. As I said, when you're really pushing the boundaries computationally, you might make the quark masses heavier than they are in nature. Almost all of these calculations have been done with larger than physical quark masses because it's the only way they're feasible. Physical mass calculations we started in 2021 and we're still taking data. So you'll see results in the next few years on that front. But I want to give you some examples, focusing in on really this question of the structure, the quark and gluon structure of protons, neutrons, and nuclei. When it comes to nuclei, the question is really, how different are nuclei from a collection of protons and neutrons stuck together? That's how we like to model them. What's the difference really when you start looking into the quark and gluon structure? Now that's encoded in quantities with names like EMC effects and exotic blue that I'll show you on the next couple of slides. So this cartoon really highlights what I'm showing here. This is a fairly typical picture of what a nucleus looks like. You draw a number of balls, which are supposed to be protons and neutrons, and inside them are the quarks and gluons, and they get stuck together, right? So the question is, how is this picture modified? Now, these types of nuclear physics effects are called EMC effects, after the European muon collaboration, who saw in 1983 for the first time that deep and elastic scattering, remember that's the process I talked about right at the start of the talk, fire an electron at a proton and break it apart. But deep and elastic scattering off a nucleus is not the same as deep and elastic scattering off the protons and neutrons that make up that nucleus. And that's what you're seeing here in this figure. This is the deep inelastic scattering cross-section ratio per nucleon for iron to deuterium, so two different nuclei. This is a longitudinal momentum fraction of the struck quark, and this is not 1, is what you're supposed to be seeing from this figure. This is saying there is nuclear physics in here. So the question is, how do these types of nuclear physics effects arise from the underlying quark and gluons and the standard model physics? Now, as I've alluded to, nuclear physics calculations are extremely difficult, but there's also not a lot known about some of these questions, and so even calculations with large uncertainties can give us new information. So what I'm showing here is the momentum fraction ratio of helium-3, so a fairly small nucleus with 3 protons and neutrons, to the proton. Remember I showed before an example of the momentum decomposition of the proton, and I showed you how much of the proton's momentum comes from up quarks, down quarks, strange quarks, charm quarks, gluons. Now I'm showing the ratio of the up minus down combination in helium-3 to the proton, and the up plus down combination of helium-3 to the proton. That's what this figure is showing. This band here is the theory calculation. Now, you can see a fairly large band that is not inconsistent with 1. And so you say, okay, we're not really resolving a nuclear effect here at all. Why is that interesting? And the answer is because that is still a better constraint than was possible experimentally. So experimentally, you have this blue ellipse. And if you include just that one data point from a Lattice QCD calculation, this red band, into that calculation, and this was extrapolated to the physical mass and so on, you go from the blue ellipse down to the purple. And so even with the very first principles calculation of a nuclear effect like this, we've been able to combine with the experiment and improve our understanding of nuclear structure. So this was the first demonstration of this sort of a pipeline. I find it very exciting. Seeing a number different from 1, you might not find that very exciting. So here's another example where you actually see a nuclear effect. This is what's called exotic glue. So this was postulated by my colleague Bob Jaffe back in the 80s, that you could have gluonic contributions to nuclear structure that cannot be associated with the individual protons and neutrons inside that nucleus. So thinking about that as an operator, I have an exotic glue operator whose expectation value in a single proton or neutron has to vanish. This is a purely gluonic thing, but its expectation value in a nucleus might not vanish. And so you should picture this as contributions to the nuclear structure that do not look like this, but in some sense look like this. So gluon contributions to really the binding of that nucleus together. Now this has never been measured, it had never been calculated, but we were able to get a first signal for exotic glue. Technically the observable is called gluonic transversity. I can explain that later if you're interested. But in a deuteron, so in a light nucleus. And what I'm showing here is raw lattice data. And here I really get to play experimentalist, right? What you're looking for is a bump. That bump should be to the left of that red star, and it should have a very characteristic shape given by this gray band here. And as you can see, the data fits that shape. And if you do a statistical analysis here, you can rule out the hypothesis of no bump to better than 1 part in 10 to the 12. So you can very definitively say there is a signal for this effect. You'll notice I didn't put numbers on these axes here, and that's because I didn't want anyone to look at that and read a number, because these calculations are not systematically controlled. That's also not what we were going for. We were going for, is there a signal or not, right? And there is. So we've sort of seen the whole spectrum from high precision calculations, where you can really decompose the proton's momentum with percent level accuracy, through to questions that are really qualitative. Does this effect exist in QCD or not? Right? The full spectrum here. So this hasn't been measured. There's a letter of intent to try to look for this in an experiment at Jefferson Lab. So hopefully we will see. Okay, so those were really some examples of the structure of matter in some sense for its own sake. What does the proton really look like? But also, of course, this is important for backgrounds and benchmarks for searches for new physics. And in the interest of time, I'll give just one example. Happy to talk more after, I can give you many. But dark matter. Dark matter is, of course, really one of the big questions of our age, right? There's abundant evidence for something, and a good explanation of the something is that there is matter interacting gravitationally but not emitting or absorbing light. Everything from, so this is the Coma cluster, that's a large cluster of galaxies near Earth, and as far back as the 1930s it was recognized that something doesn't quite add up. It's like something's acting gravitationally to hold that cluster together that you can't see. It shouldn't be sticking together like this. It's like there's additional non-luminous mass. Bullet cluster and all of the similar pictures that have been taken since then. So a famous false color picture where we're able to really see clusters of galaxies collide. And the color separation is really here in pink, the luminous matter, and in blue, the matter that you can infer is there from gravitational lensing. And you can understand how such a separation can come to be, is if you have clusters of galaxies with the matter and dark matter sort of in similar places. As they collide, the regular matter collides, and the dark matter continues on through, and so you get a separation like you see here. Galactic rotation curves. So this is the center of this spiral arm galaxy moving out along a radial direction. This is the velocity, how fast things are moving. The velocity you measure is much larger than it should be from the visible disk. It should be flying apart, not sticking together. All of these things add up and give us evidence for something. And we want to know what it is. And of course, there are many, many, many theories for what dark matter could be. From extra dimensions, extra Higgs particles, extra axions, supersymmetry, everything possible under the sun. And so we want to constrain this space of possibilities. Theorists are creative. There are many ideas. How do we rule some out and have support for others? Many ways. Just one way is through dark matter direct detection experiments. So you take a detector here on Earth, terrestrial experiment, you look for dark matter to interact, and one thing that you could see is if it interacts weakly, that is via the weak interactions. So if dark matter is a type of dark matter that interacts with regular matter through the weak interactions, you could see it in these types of experiments. So then the question is, I've not seen dark matter. Which of those theories does it rule out? Well, the detection rate depends on the properties of the dark matter. That's what we want to constrain to rule out some of these theories. But also the probability for the interaction with a nucleus, right? These detectors, typically you use nuclei because that's something you can assemble en masse here on Earth, increase the cross-section by making a very big detector with very many large nuclei, right? And when you look at the types of exclusion plots you get, so this is a figure showing limits on WIMP, that means weakly interacting massive particles, so a dark matter candidate interacting with normal matter through the weak interactions. Nucleon, that's a proton or a neutron, interactions from direct detection experiments. This is the interaction cross-section. SI just means spin independent, right? This is the mass of that hypothetical dark matter particle. Each of these lines is saying this experiment was run and it excludes everything above the line, right? So this looks okay. We've taken experiments, we've ruled out some of these possible dark matter candidates, but this is really the sticking point here. You see, this is the cross-section for the interaction of your dark matter candidate with a proton or neutron. That's a nucleon. I just said the experiments typically use very large nuclei. things like xenon are pretty common, right? So there's been a translation in making this figure from not seeing dark matter hit xenon to what that means for how strongly dark matter interacts with a proton or neutron. Well, so how do you do that translation? The simplest thing is you use what's called the Born approximation. You say, well, the dark matter is going to hit a single proton or neutron in a nucleus at a time. And so you take the number of protons or neutrons and you multiply that by the probability of dark matter interacting with a single proton or neutron. Now, I've said we're in a precision era of Lattice QCD for Proton. You take a model of dark matter, Lattice QCD can calculate this interaction for you, whatever your model of dark matter is with a single proton or neutron, to high precision, no problem. But okay, what if that's not the only term? What if it interacts non-trivially with multiple protons or neutrons in a nucleus at a time? Well, this isn't known. You can't measure it. You'd have to, say, use something like dark matter scattering to measure it, and we're looking for that. So how do you get it? Well, you might try to compute it from first principles calculations. And in the last few years, actually, we've been able to see that this may be much more significant than you would otherwise expect. So we don't know what the microscopic theory of dark matter is, right? But the limit of a generic spin-independent interaction is scalar. So if it's a spin-independent interaction of dark matter with normal matter, then what governs that scattering are what are called scalar matrix elements. Okay. Now, what I'm showing you here is a comparison between that nuclear physics effect, that multi-body effect, in the scalar matrix elements relevant to dark matter with weak interaction matrix elements. I've used the weak interaction matrix elements here as the comparison because they're easy to measure experimentally. You can go and measure the nuclear effects in them, right? And what you're seeing here, this is the percentage nuclear effect. The blue is our Lattice QCD calculation, which was at unphysical parameters, right? Few percent nuclear effect. This is in helium-3, a fairly small nucleus where we're able to do that calculation. You extrapolate to the physical point, you get this green, so a few percent nuclear effect, from a fraction of a percent to a few percent nuclear effect, which agrees beautifully with what you measure experimentally for the nuclear effect in helium-3. If you go to a medium mass nucleus like tin, you can measure experimentally that you have a few tens of percent nuclear effect. Okay. What about the scalar matrix elements? Well, our Lattice QCD calculation already sees an order 10% nuclear effect. Does it have to follow the same pattern that this gets bigger in nuclei of the same sort of mass like xenon? Not necessarily. There's no good reason it shouldn't either, right? And so what this tells you is this is really an unexpected difference, an unexpectedly large, by a couple of orders of magnitude, nuclear effect in the matrix elements most relevant to dark matter direct detection experiments. And so this really says, well, you really want to be able to get this under systematic control. What does this really mean for dark matter direct detection experiments on xenon? So, how do you do this? Well, we can't do calculations directly in very large nuclei. I said that's a factorial times an exponential computational problem. So what you can do is build a pipeline that takes advantage of the fact that we do know that a fairly good model of a nucleus is a collection of protons and neutrons, right? So you can start from there and then build on the correction. So you can say, let's use a nuclear effective field theory where the one-body effects like this, that's dominant. The two-body effects, remember I said 10% was unexpectedly large? Okay, well it's still 10%, right? So you can really expand. You can say the two-body currents are subleading, but maybe non-negligible. You can determine these from very precise Lattice QCD calculations in a proton, these from slightly less Lattice QCD calculations in a light nucleus, constrain the 2, 3, 4-body pieces, and then use the nuclear effective theory to match to many-body predictions to make predictions for large nuclei. And if you do that for the weak interactions on the other slide, you get consistent results for tin. So the only question is, how do we get the scalar calculation under enough control to follow this same matching procedure? Right. Okay, so that's really the potential I see here in first principles calculations for nuclear physics. Both we can learn more about the structure of nuclei sort of for their own sake than we can experimentally. It can really be complementary, but also it's necessary to really place limits from various intensity frontier searches for new physics on the new physics. Okay, so I keep saying, oh, we'd really like to do a calculation in xenon, but we can't, right? And this is sort of a common theme here. Not just dark matter directed detection experiments. Say you'd need xenon, that's atomic number, the number of protons is 131. For other interesting searches for new physics, if you look at double beta decay, the process I mentioned before, where you're looking to see if the neutrino is its own antiparticle or not. The lightest nucleus that does that is calcium, that's A equals 48. Still a lot bigger than the 4 we can get to, right? Argon is what's used in the DUNE. So this is the flagship long baseline neutrino experiment happening in the United States now. It's under construction, where they're firing neutrinos at an argon target to really get the mixing parameters and the mass hierarchy. You'd like to be able to do calculations of, in this case, axial form factors of argon, A equals 40. Still too big, right? And this is the case even if we use this pipeline of matching to effective field theory and many-body calculations. You really need higher precision, tighter systematic control, and so that you're facing exponential and factorial computational challenges in doing that. That really motivates the need for new algorithms, right? If you have an exponential standing in your way, you don't try to take exponentially more samples, you try to write down an exponentially better algorithm. Okay, so that brings me just to the last part of the talk, which is how advances in computing and algorithms are sort of feeding back in to this loop. Now, a very natural question is, what about machine learning? We have calculations that demand extreme scale computation. They're systematically limited by the amount of computation available. Can we accelerate them via advanced AI or ML? Okay, now one particular part of the Lattice QCD calculations that I want to talk about this question of can we accelerate via AI or ML is simple to understand. It's just the sampling problem that happens at the start of every Lattice QCD calculation, whether you're studying the proton or a nucleus. I said we're doing very high dimensional integrals by sampling, right? So you have to say, I want to generate some set of samples, they're called field configurations, with a known probability distribution. In our case, that's the exponential of the action describing the quark and gluon dynamics. But at its heart, this is just, I need to take samples according to some known distribution. And this is the first step of every calculation. If you want to visualize that, you can visualize the field theory samples like this. And what you're really saying is, I want to take samples like this, where there's some sort of characteristic correlation scale, much more frequently than samples like this. This is just random noise. This is very unlikely. These are likely. I want to draw these samples more frequently than these, right? This sounds like something you can do with machine learning. It sounds like there's a direct analog to a problem that's been very successfully tackled with machine learning, which is generation of fake images. If you say, I want these samples often, and I don't want this random noise, that sounds a lot like the problem if I want these pictures of people's faces. These are fake faces, of course, AI generated. I want these often, and I don't want random noise. Right? So can you apply the same sort of techniques that have been very successful for this problem to this problem? Of course, as soon as you stack up that comparison, you see that there's similarities, but there's also a lot of important differences. So the first is, it's only the set, the ensemble of these gauge field samples that has any meaning at all. They have to follow a known probability distribution. Whereas pictures of faces, well, each face is good or not on its own. Is that a good picture of a face? Or can you see that there's some defects in it, right? Different target, distribution versus individual quality. Secondly, there's an extreme inversion of the typical data hierarchy. So in this sort of benchmark image set for machine learning, each image is described by something like 3,000 numbers, and you might have 60,000 samples available for training. We have each image described by something like 10 to the 9 to 10 to the 12 numbers. Those are our field theory samples, and you might need order thousands to do your calculation. This ratio is sort of an inverse of this ratio in an extreme way, right? So it means that anything that needs training data is not going to work, right? That's a lot of typical machine learning algorithms. Then you have other differences. So long distance correlations are really what drive the physics. In images, local structures are important. The nose, the eye, and a picture of a face, right? You have interesting symmetries that just don't exist in the image context. So as images, these are quite different. You don't usually let your image rotate across boundary conditions, right? As gauge field configurations, these are exactly the same, and they encode the same physics. That's fairly simple, but it gets more complicated. There's also internal degrees of freedom. And so really these gauge field configurations are represented by matrices on every edge of the lattice. And there are transformations called gauge transformations of those matrices that take you from an image like this where every edge has exactly the same matrix to one like this where every edge has a different matrix, but these are still identical from a physics perspective because they're related by this symmetry. So there is no analog of this in the image space at all, right? So it becomes clear very quickly that even though there's a clear analog, there are clear differences. You can't use anything that exists for other purposes. You have to design machine learning algorithms from the ground up for this purpose. And of course, there's a Boston area institute, the Institute for Artificial Intelligence and Fundamental Interactions that both MIT and Harvard are part of, where we're really trying to push this question of how do you design machine learning from the ground up with the physics built in for physics problems. Okay, so in the, not the next lecture, but the Thursday lecture, I'm going to go into this question in a lot more detail. I'm really just giving you a teaser here. But one thing I want to make clear is I'm talking about machine learning for theoretical physics calculations. So there's one thing it can do for me, and that is get the answer faster, right? I'm doing an integral. If the answer to your integral is 2, you better get 2, whether you're using machine learning or not, right? There's no, I'm not searching for structures, I'm not, pattern matching. I'm just trying to get an answer that's given by the equation of my theory faster than I can via a conventional algorithm. So it has to be exact, right? So I need mathematical guarantees of exactness to preserve the fact that I'm doing a first principles theoretical physics calculation. So you have to design an algorithm that has this feature here, where if your algorithm is poorly trained, you'll get the right answer. If your algorithm is well trained, you'll still get the right answer, but hopefully it will be much, much faster, right? That's how you guarantee exactness, is you create this scenario where even before training, it will be exact. It just might be very, very slow, so slow that you wouldn't use it. So how do you do that? Well, just to give you a sense for it, there's several ways. So the first is really the least interesting. It's you do the calculation the same way, but faster. And that is maybe you have some underlying parameters in your algorithm itself that can be tuned to optimize the calculation. So we go from the start, the same start, to the same finish, which is our provably exact theoretical physics calculation. But instead of our algorithm walking along, it's now speeding along because we've tuned the parameters. For an explicit example would be if you want to invert matrices, there's a very nice algorithm called algebraic multigrid, which does this very efficiently, but it has a lot of free parameters. And so there's a lot of space for tuning those parameters to make the algorithm efficient. And optimizing those with machine learning is a very efficient way of getting more performance out. So, okay, it works, it's not so exciting. Another way is, well, in the end, you're going to use the same guaranteed exact algorithm to solve your problem, but first you're going to change your problem into one that's easier, right? So now it's the same algorithm walking along, but we've made the road shorter. So this is, examples would be preconditioning of any type. So some sort of pre-processing step you can do to make your problem easier. Or a change of variables is a good example. One that I really like to use is an example of a complex integration. You know that no matter where you put the integration contour, as long as you don't cross a pole, it'll be the same answer. So what if you can put the integration contour somewhere where the computation is much, much, much easier? Well, then you can change the problem, run your standard algorithm, get the exact result much more efficiently. And it's guaranteed to be exact because all you've done is deform your contour, right? Another example is, well, maybe you have a very efficient way of solving a slightly different problem, but you know how to fix it up in a provably exact way, right? So this is, for example, you could sample a different probability distribution than the one you actually want. But if you have a rigorous way of correcting, then if you've sort of teleported this part, maybe this last part of the road can be done with a conventional algorithm very efficiently, right? So I have examples of progress in Lattice QCD for all of these three topics. In the lecture on Thursday, I'm going to talk a little bit more about an example for this topic here, but I'll give you just sort of a hint of the flavor of that here. So for this sampling problem, you can do exactly what I just said. What if you can sample a close probability distribution very efficiently and then correct it? One way of doing that is through what's called a flow model. It's a type of generative model, but the idea is very simply a change of variables. You say, what if I can map from a very easily sampled distribution, think something like Gaussians. Gaussians are easy to sample, right? To the complex distribution I actually want. Well, if I have that map exactly, I've solved my sampling problem. I just take Gaussians, lots of Gaussians, put them through my map, and out come the hard samples that I was struggling to generate, right? If you have certain features of this map, in fact that it's one-to-one, it has a tractable Jacobian, there are known algorithms for fixing up the fact that this might not be exactly the distribution that you wanted. So as long as this approximates your target distribution, that's good enough. And so then this is a problem that lends itself to a machine learning approach. You say, can I parameterize this map as a function with many free parameters to be optimized, optimize them using machine learning methods to get as close as possible to this sort of free sampling approach where I just sample the easy distribution and out come the samples of the distribution I want. This is something we've been working on for a number of years now, and we're getting, further and further. We've reached QCD, further and further towards the end. But to give you an idea of just what I mean by develop from the ground up, well, flows have been typically designed to work on real numbers. We have variables that actually live on compact connected manifolds. We have gauge field degrees of freedom. So the simplest example of a compact connected manifold is a circle. And so at the very start, we had to go back and say, well, how do you actually design this type of machine learning for variables that live on circles? So we're interested in this for our theoretical physics calculations. It turns out that's also interesting if you want to do, think about a multi-jointed robot arm. The positions of the joints are defined by variables that also live on compact connected manifolds. So it's useful in other contexts, but we had to sort of invent this for the QCD application. Okay, circles, that's not quite there yet. What about the symmetries of the theory that I talked about building in? In fact, if you have a way of correcting for exactness, you don't have to build the symmetries in, but when you have a very, very high dimensional symmetry group that's a 10 to the 12 dimensional symmetry group in a 10 to the 12 dimensional sampling problem, you have to build them in because it's just not computationally tractable otherwise. So you can sort of see, if I have this flat direction here, it's much more efficient if that's directly built in rather than trying to mock up the flat direction in my distribution by learning it, right? So you have to build machine learning architectures that have the symmetries, the complex symmetries of QCD built in them directly. Once you do that, you can already start to see the potential of this approach. So this is for a very simple field theory. It's not QCD. This is the cost for independent samples. And this is changing the parameter of the theory towards a direction where the conventional sampling becomes much more expensive. These are conventional sampling approaches. You can see they become exponentially more expensive, moving to the right. This is the machine learning sampling approach. You can see over here it's orders of magnitude more efficient than the conventional approaches. Okay, so not QCD, simple theory, but it sort of gives the idea of how this could work. Then you have to say, well, what about multimodal distributions? How do I really sample them? In practice, what's the difference between in principle and in practice guarantees of exactness when you have a multimodal distribution? If it's exact only in the limit of an infinite number of samples, that's not useful in a practical sense. So you need both. You need a in practice and an in principle guarantee of exactness. What about fermions? So fermions in field theory are anti-commuting variables. So how do you deal with these sorts of anti-commuting variables? How do you design machine learning architectures that can account for those? Once you do those, you see that this approach continues to work. So here we have a theory much closer to QCD. This is some particular observable. It's the chiral condensate, but it doesn't matter what it is for my example. This is a conventional sampling approach that, as you can see, at these parameters, it gets stuck. And it gets stuck in sort of one part of the distribution. It can't cross a potential barrier. And so even though the uncertainties go down like root n as you increase the number of samples, it's converging to the wrong value. The machine learning sampling approach, however, converges directly to the correct value here. So what's left? Well, what's left is running it at scale, which we're doing pretty much right now. So Aurora is the new largest supercomputer in the United States. And we have early science time and have just got access to try to deploy these algorithms for QCD at some sort of scale for these physics problems. This is sort of a hope for the future. So what do we have, really? It's machine learning accelerated sampling that's provably exact in the limits that matter, that's orders of magnitude more efficient than conventional sampling, and that gets you unbiased results in regions of parameter space where conventional algorithms fail. So those are the different pieces that have been demonstrated. And deployment for the state of the art is scheduled sort of starting now, and we will see if it works at scale. So again, why? are we taking this detour to design new machine learning algorithms with physics symmetries built in? Well, it's really motivated by all of the physics that I described. If we want to really overcome systematic limitations, so some of these brand new calculations, the gluon structure of the proton, right, they're really pushing what's possible computationally. There's going to be new predictions from an electron-ion collider. We'd love to make theory predictions before that machine comes on. We're pushing the boundaries computationally. Mu on G minus 2. There's that interesting tension between theory and experiment. How do we get first principles theory calculations to compare? Higher statistics. We want to do controlled calculations of nuclei, ideally going a bit bigger than A = 4 for direct detection experiments, nuclear reactions. Again, if we can have accelerated algorithms, that really opens the door in all of these directions. Okay, so to conclude, I want to give you sort of a summary of the story we've seen. So first principles calculation of proton and nuclear structure are really giving us a new window. So I gave examples of the pressure distribution in the proton, where just within the last year, we've had first theory predictions confirmed by first experimental measurements of new aspects of even qualitative questions, like the gluon radius of the proton, that we never had the answers to before. But also things like backgrounds and benchmarks for searches for new physics beyond the standard model, including even nuclear effects. And as we sort of continue to push the boundaries here on the physics side, there's a lot of excitement about a new generation of provably exact machine learning accelerated algorithms that might break through some of the conventional computational ceilings and enable this to go even further as we try to understand the structure of most of the matter in the universe. Thank you.
That's a really great talk. It's just more like a curiosity for these like Aurora simulations on these big computers. I don't have much experience on them. How long does it take to run them in these big machines? And do you work with the engineers to optimize things on the local hardware?
Yeah, so, okay. State-of-the-art calculations that we're not currently running on Aurora, sort of on more established architectures, they'll often run over many years on many machines accumulating data. So 5 years, 10 years. What we're doing on Aurora is really trying to scale this up for the first time. So this will be a short window of early science time over a few months, but we've been working since 2019 to try to get codes ready to run on that machine. And there is, so we have sort of an early science project which gives some support and an interface with, you know, hardware vendors as they assemble the machine. But a lot of the work's done by my group, who are not computer scientists. So a lot of physicist optimization of code sort of in conjunction with the people benchmarking the machine as it gets put together.
And if I could ask a second question, you were talking about direct detection earlier and these nuclear terms, and you were saying that maybe the second order terms could be large, for example, like xenon. When you say could be large, is that like, could you think it could be more than an order one number? Because the variance in those constraints look like a factor of 2 or 3. So are we looking like those effects could be order 1, or is it like more 10% level changes?
No, so the fear is, of course, that it could be more like order 1 than 10%. So from the weak interaction example, you have a sort of a few percent in a small nucleus goes to 10% in a larger nucleus. And in the scalar interaction relevant to the dark matter direct detection, we already have tens of percent in a small nucleus. And the question is, if that continues to increase in the larger nucleus, maybe it could be order 1. Of course, it could also go the other direction. The point is just that there's a very large uncertainty on how big those nuclear effects are, because they are certainly very different than what we had expected before they were calculated.
Right. And you mentioned, and I will give you the mic authorities, and you mentioned that you're going to do this EFT.
Yeah.
But doesn't that preclude that the effects are by construction small when you do the treatment?
Well, the individual, so the two-body effect can be small, but then the cumulative effect of all of those separate two-body interactions in a large nucleus can be larger, right?
Okay. Thanks.
Any other questions?
Thank you for the talk. I also have a question about this two-body currents. So I wonder in Lattice QCD that what do we compute? Because when I look into literature for dark matter detection, usually they match to non-related EFT or Cal EFT and compute the matching coefficient. But I wonder what do we compute in Lattice?
You would compute the matrix element of the relevant current. So for a spin-independent interaction, you would calculate a scalar matrix element in a nucleus. So you would calculate it in a proton to get the one-body piece, in a deuteron to get the two-body piece, in helium-3 to get the three-body piece, ideally in helium-4 to get four-body piece. And so you'd separate out all of those matrix elements, and then you could take those and you could match to your effective field theory to match the low energy constants.
I see. So when we consider, let's say, a dark matter detection, we need to use EFT to describe that process and then pick up those individual building blocks and put it into, pass it to the Lattice QCD. Exactly.
Yeah, that's right. That's sort of this pipeline. You would take the EFT, you would say, well, what are the low energy constants, and then constrain those by Lattice QCD calculations of matrix elements.
I see. Okay, thank you.
Right. Can you say something about current observation of proton decay and why it is a viable idea or why it is not a viable idea?
So experimental observation of proton decay, I'm not up on that literature, unfortunately.
Is it a viable idea?
The students asked me at lunch about whether supersymmetry is a viable idea. I feel like my answer's sort of similar. Ideas are great until they're ruled out.
Yeah, thank you for the talk. You mentioned deforming the integration contour to find a better convergence region. So if I have a small number of dimensions, I can deform in the complex plane and go along steepest descent contours or like Lifshitz thimbles. Yeah. So if we have a very high dimensional integral, is it possible to do a similar procedure or not?
Well, so people have tried thimble-based approaches for, field theories, typically not quite getting all the way to QCD, and they do work very well if you have a field theory where you can write that down. QCD is complicated, so essentially what we and others are working on is similar to that approach, but with some, parameterization of the space of contours that you're trying to get at, so you can use machine learning. But it's the same idea, exactly.
Thank you.
Oh, maybe you're going to get to this in your other talks, but can you say a bit more about what this flow algorithm is, and maybe in the context of the Schwinger model, 2D Schwinger model? I mean, is it a better way of getting the fermion determinant, or which? Yeah,
on Thursday I'll go through that in some detail. Yeah, so it's maybe it's best to describe then, but there's sort of two pieces. You can take the gauge piece, then you can do the fermion piece. You can do a pseudo-fermion approach, right, where you introduce auxiliary degrees of freedom. Basically the flow has to be a one-to-one map. So the question is really, you define all of your field degrees of freedom, and then how do you write down the map that obeys all of the symmetry constraints you can? So for the fermion piece, for example, you want to build in a parallel transport invariance, right, between the fermion fields. So you have the fermion field and the gauge field, and you want to respect that symmetry, that if you have the fermion field and a gauge link, and you transport the fermion field. So you can build a parallel transport convolutional neural network piece for those fields.
So that's the machine learning part, the transformation. I see.
That's the machine learning, the part of the machine learning transformation for the fermions. For the gauge field, it's a similar question. How do you build in a gauge symmetry or into the transformation of those field degrees of freedom?
Thanks.
Hi, thanks for the talk. So just going back to the interaction with dark matter nucleus, you said there's a motivation that was showing that these cross sections might actually be markedly different than we would think. Was that what you were showing in the plot, just comparing with the helium and the? Okay, so that's it. So there haven't been any initial calculations with heavier nuclei yet.
No, nothing released yet. And so on the scalar matrix element side, you would also have seen that I had a blue band and a green band, and I was showing only one of them because also the extrapolation to the physical quark masses hasn't been done on that side either. So it really is a question mark on which way that extrapolation will go.
Hi, thank you. I really enjoyed all the examples of the interesting physics questions that we can answer and started to better understand with Lattice QCD. My question is there a question that you can pose and answer with Lattice QCD that could help us to understand the process of hadronization?
Yeah, I mean, yes. What you can get at from Lattice QCD are essentially matrix elements. So no matter what you want, the question is then, can you write down matrix elements that you can relate in some way to the process that you're interested in? So you can build up to something like hadronization or fragmentation by thinking about, well, what about parton distribution functions and transmission-dependent parton distribution and fragmentation functions? And so there's been a lot of development in the last few years on how you say, well, if I have writing down something where the matrix element is really has a light cone separation, how do I do that in a Euclidean spacetime, right? And so in that case, you come up with something that say, well, if I write down something that is rotated off the light cone, but in some limit, say like a limit of infinite momentum, returns to the light cone, then you can write down a large momentum effective field theory expansion to match between what you can actually compute on the lattice and what you can, what you're really trying to get at. So that long-winded way of saying is that difficult directly, however, writing down matrix elements that can in some way be related to the processes you're trying to constrain, yes, there are some constraints you can make.
Well, let's thank Fiala again for this wonderful lecture.